So I'm happy to introduce the first speaker for the afternoon, Cheol Hyun Cho, about the unit normal correspondence for a monotone divisor complement.
Thank you very much. Thank you very much for the invitation. I'm enjoying Miami so far. I was here last week too. Okay. So let me start with the motivation. So let's say X is a monotone integral symplectic manifold. Okay, monotone means that the first term class of the tangent bundle is proportional to the symplectic form, and integral means the symplectic form lies in the integral formulus class. Okay. Now inside this monotone symplectic manifold, we have a divisor, monotone divisor. So this is monotone. Smooth. Symplectic hypersurface. Okay, inside X, and such that the usual is donuts and hypersurface assumptions, so that the Poincare dual of this D inside X is K times the symplectic form of X. Okay. And also it's monotone, so it has this monotonicity constant, which is the Jeong class of D, of tangent bundle of D is tau D times symplectic form on D, where the symplectic form on D is just the symplectic form on X restricted to D.
When you write the multiple class equal to a symplectic form, you mean the class of the symplectic?
Yes, yeah, that's always what I mean. And you can easily compute that tau X minus K is tau D. It's normal direction and tangent direction and so on. All right, and it's known that for sufficiently large K, it's called Donaldson hypersurface. So for sufficiently large K, we have such symplectic hypersurface, and it's so that the complement is because somehow symplectic form becomes exact on the complement. So this is Liouville, becomes a Liouville manifold. In fact, Weinstein manifold. Okay, so let's denote the complement as M. In fact, if this is divisor D, maybe let's say we have a normal bundle. This is MD, this is normal bundle. And maybe take the length part, the length is less than 1, so it's disk normal bundle. Okay, and so instead of taking out D, I can take out the disk normal bundle of D. So this is D and some neighborhood of. So instead of just taking out D, I'll take out the neighborhood of D. And this is then this maybe it's better to call it Liouville domain because it has a boundary which is given by this length 1 part. Right? Okay, so this is the setup. And the question we are interested in is the relation between the Fukaya category of M and Fukaya category of D. Okay, so this is ambient space. This is space X. So question is Fukaya category of M. So this is x minus d. Correct. And this, there are some several studies on this thing. So, for example, some cases, it's known that the category. So, sorry, so this is wrapped Fukaya categories because M is trivial, non-compact. In some cases, this wrapped Fukaya category of M divided by compact. So this means F means compact Fukaya category of M. So it's expected that Fukaya category of D is, so I mean, if you kill, I mean, so the boundary is, so this is boundary of M, and this part is M. So if you kill something in the compact region, then you should get something in the at the boundary, and so the heuristic of this is on the wrapped category of M. If you kill something compact, you should get something on the boundary. So that's rough idea. And this is also, this is called stable category. And then, am I right? Is the name stable? And there is also Rabinovich, you know, with category by Ganatra, Gao, and Venkateshi. And so this is known to be isomorphism if there is a causal duality. So somehow you there is, so somehow if you take some quotient or if you do something else, then somehow you want to recover this category of divisor. And what we want to do is we actually want to.
So there is a map from the quotient.
This map?
No. Yeah, from the
Oh,
quotient to the
yes.
Rabinovich.
This map exists. There is a map in this direction.
There is a map.
There is a map, and it's isomorphism. Something like this causal dual, whatever it means. In some nice cases, this is known to be isomorphism. Oh well, let me just erase. In some cases, nice. But we are not going to use these ones. What we'll do is we are going to define some category, C, gamma, sigma, and the functor. And there is a functor from Reeb. Okay. Of course, if you compose, you will have functor this, and somehow, so this map will be some kind of Lagrangian correspondence, and often not an isomorphism because, as you see, I mean, somehow you need to kill something to have an isomorphism, and this thing will, so this kind of quotient will kind of happen here, and sometimes we expect this to be an isomorphism. So that's today's talk is to explain what this is and vice versa.
And do we have three notations of the Fukaya category?
Oh,
Yes, it's all the same, yeah?
yeah. Did I fix everything? So this F compact means F. All right. Any other questions? So let's see, just to not get lost. So let's see an example. In P3, consider a quadratic vector surface B. And this one is just nothing but P1 plus P1 times P1. And it's known that this is P3, and there is this D. And the complement is, in fact, it's Weinstein. So you can kind of shrink it and look at the skeleton, isotropic skeleton. And in this case, the skeleton is RP3, so you have RP3. So this is T star RP3. And also, Biran and Kapnevsky also show that if you take out RP3 from P3, then you should get this normal bundle of D. So if we take this out, it becomes normal bundle of D. If we take this out, it becomes cotangent bundle of RP3. This is the situation. Okay, and then so just to have an example, to see an example, let's consider a cotangent fiber. So this is a cotangent fiber. So cotangent fiber goes to infinity, and it's going to D, and so somehow the limit or the correspondence we define will become either the image in D will be the anti-diagonal. So let me skip this part, but anyway, so here it's going to be diagonal. Z bar in P1 cross P1. So let's accept this. Then okay. So now the relation is now comparing. We are comparing wrapped flow homology of this cotangent fiber with flow homology of this anti-diagonal. So wrapped flow homology of T star P RP3. This is the correct one. And I want to compare it with the flow homology. This is Lagrangian. So this anti-diagonal is Lagrangian in P1 plus P1. So this is Lagrangian flow homology of this anti-diagonal.
What's the Fukaya of a parabolistic of two?
So this means the home space between in the wrapped Fukaya. So wrapped flow homology or self flow homology.
What's the little t? What is the little t?
This is just point.
Which one?
Just some point. Well,
no, but I mean, this picture is like you have ES.
So it's okay. Let me not.
So just if you just mark the point of the intersection with P, I think you will be happy.
Yeah. No, but which? It's very specific.
I don't choose
Any of.
Okay, anything. But anyway.
But you will see the group action, right? This is the Lie group, right? So this is that somehow used the fact that
Let's not go into details.
okay, I'll talk to you. Thank you.
But there's a fiber, right? I went from RP3 to the diagonal. So the diagonal seems to be two-dimensional real. So real 3 to real 2?
Yeah, so this is going to be a Lagrangian correspondence. So we'll also talk about this.
Yeah.
Okay. All right. So what's the generators here? So generators here are there's identity and there is x. So this x is so 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 in IP3 you have a sphere. I mean there is a kind of loop which go around IP3 twice, or in S3 there's just going around once. So this is like a point class of S1. What I mean is on S3, in S3, you can go around this sphere once, right? And in fact, in whichever direction you go, there is a sphere. So I mean, there is a circle. So this generator comes in kind of S2 family, and so S2 has a point class and fundamental class. So this is the point class, and X square corresponds to the fundamental class. This is fundamental class of this kind of orbit, and there is Y, which is because it's RP3, you don't have to go the whole rotation. You only go to the antipodal point, and this is the point class of half rotation, and there is yx and yx squared and so on. All right.
I'm sorry, do you mean by point class of S2?
Point class of S2. Yeah, thank you. Yeah, that's what I mean. So on RP3, the tangent space is like R3, and the unit like length 1 vectors define S2. So that's kind of how many kind of S1 orbits you have, and among this S2 worth of orbits, this is the point class and fundamental class. All right, so whatever this is, this looks like there's x, y. This looks like a polynomial ring divided by y squared equal 1 for some reason. This is anti-diagonal in P1 cross P1, and it's well known that this is isomorphic to anti-diagonal has the same as the flow cohomology of P1. So this is flow cohomology of P1, and this is well known. So we have some Novikov ring, and this divisor class H, such that H squared equal P. So this is quantum cohomology of P1.
Sorry, I think I missed what is HF of the supplementary class.
This is Lagrangian flow homology, and this is flow homology of symplectic manifold.
So
Lagrangian flow homology of the diagonal with itself is same as symplectic flow homology of this. Okay. This is a general fact because this is diagonal, so you will have typically like the disk with Lagrangian boundary condition on diagonal. You can kind of it's n%, so you can kind of rotate it and glue. You get a sphere. So disks here correspond to spheres here, and that's somehow what's going on. All right, so there is. So the question is, what is the map between right?
So the HF star of P1, that's Hamiltonian?
Yeah, this is Hamiltonian. Yeah, this uses quantum cohomology. Quantum, maybe sure. Quantum cohomology.
Too many HFs.
Yeah, so, yeah, that's maybe clear. Quantum cohomology. one way to go from left to right is you can first switch to Novikov ring. So this is some Novikov parameter, formal parameter t and t inverse given. It's monotone, so we only need polynomial ring. And so just switch to lambda variable. And the target is also lambda variable. And you just define the map x to be ht inverse, y to be ht minus 1/2. Strangely, so this one, usually this t corresponds to simplex somehow this area, I mean the whole class of the sphere. But to define this map, we need this 1/2. This 1/2 is somehow related to a vector integer coordinate of this. But okay, let's say instead of this, we extend this to like allowing this formal parameter to have this half integers. If you do it, then this y squared equal 1 relation goes to h squared times t to the minus 1, and this becomes 1 under this relation. So there is a map. So this is a homomorphism. This defines homomorphism. And of course, this is not an isomorphism because you have one generator here and you have two generators here. This is not an isomorphism. And so what you can do is you can further divide it by strange relation t to the xy equal t to the negative 1/2. Then what happens is xy squared is now they are commutative variables and y squared equal 1, so this is same as x squared, and this is supposed to be same as t to the minus 1. Right? So somehow x is kind of invertible. So you can define x inverse, for example. So this further quotient you can identify it with lambda. So using this relation, I can get rid of y. So y is t to the minus 1/2 x inverse. So x inverse is t to the tx like this. Well, you don't have to follow the calculation, but at the end of the day, what I get is lambda x divided by x squared equal t to the minus 1. So we can get rid of y variable. So this now looks very much like this one. And so the map sending x to ht inverse will do the job because then this goes to lambda h squared. So this is t inverse, t is t, and this you can fix it by just defining back in this way. So the question is, what is this guy? And what is this map? So they are these two are what I want to explain. Any questions?
So you will be able to do this generally, so this isomorphism under some assumptions.
Yeah, we can. Well, the functor is general, but the computation is another. The computation we don't know.
what does general mean?
We'll define the functor. This will be defined in the generality that I put it. For like a monotone setting, this will be always defined. The functor will always defined. But can you compute everything? Then that's kind of.
So you don't know in general how to write down this relation to make it work.
But this relation will be something intrinsic here. So that's the point of making this construction. Okay, so I think it's clear what you want to do. Before I forget, this is a joint work with Hanul Bae, who is here, and Choa and W, Jeong. Okay, so for the usual infinite structure, so we look at J-homomorphic disks or polygons with suitable boundary conditions and define infinite operation. So this is usual Fukaya category. And some of the Abujade insider introduced this moduli space of popsicles. And they have the mark points. Some of them may not have popsicles. And this was used to define Reeb Fukaya category. So to define Reeb Fukaya category, there are kind of two methods. Well, you have this kind of boundary region, and you can use some kind of quadratic Hamiltonian which wraps around near at this cone part of your symplectic manifold, or you can kind of have some slope and take a limit as the slope goes to infinity. And this popsicles was used to kind of have a telescoping construction. So telescoping construction of like slope 1, slope 2, slope 3, and they want to have everything in one complex. And these red dots are used to kind of some kind of place to put some homotopes. And the crucial thing is that the points are allowed to overlap. Well, they are on different. Well, so they are on some geodesic from mark point to the output mark point. So they don't seem to overlap. But in the limiting configuration, kind of they can go out. In the limit, you can have something like maybe 2 points go out like this, 1 point remain, and then they can collide, right? So this is kind of possible codimension non-limit. And what we want to use is the same popsicles where these are not allowed to overlap. So let me draw circles on them. So this is popsicles with insertions. And so this one, somehow these two, so the circles cannot overlap. So they have, so these two have different compactification. So what I want to say is, this one actually has very strange codimension one straightums. Like, suppose, just imagine a limit where these three of them kind of get close to each other. If they get close to each other, what happens is you get something like very thick line here, right? But because these mark points have collided, you'll have some this shape, and but you also have this points collided, so you'll also have some sphere bubble and three lines.
I can't see the difference between this insertions picture and the
This one and this one.
Yeah.
Yeah, that's what I'm trying to explain. So here, even when they collide,
the red
so
things are mark points.
just mark points, but mark points are allowed to overlap.
Okay.
So if this was allowed to overlap in this picture,
And now you replace it with stable.
you just
stable components.
yeah, just 3 points will lie
Yeah,
over
yeah,
here.
okay.
But this one looks very degenerate, right? You have this nodal point here, you have this kind of boundary nodal point, interior nodal point here. But in fact, this is codimension one. The reason is that the way they kind of the way these points collide each other and creating this disk bubble is related to the way these lines, I mean the sphere, the position of these 3 points on the sphere. So these are somehow correlated. That means the surgery parameter here are also correlated. So
It's possible to say a bit more formally what is a popsicle? Is a disk with a collection of curves and mark
Disk,
points? Or
yeah, so
what is the model?
it's a disk with interior mark points. Disk with interior mark points, but you only consider interior mark points lying on this line, connect from between the zeroth mark point and the input.
And what properties these lines need to satisfy? Is there a rigidity or I can paint it?
This line is automatically determined by, let's say it's a geodesic. It's a geodesic.
It's determined by the
Yeah, so the position of this point.
This is geodesic.
And so this point can only move around.
I see.
But the lines can move because boundary mark points can move.
Because the boundary
Yeah.
points.
So this is a very problematic stratum, and
And in the bubble, the lines are also geodesics.
yes. Well, on the sphere, it's not a geodesic, but it's some circle. If you, yeah,
Some
yeah,
some rigidity property.
yeah, yes,
Otherwise you can't paint it.
yes, yeah. If you put it on the plane, then they are like straight lines. If you put this point to infinity, they are like straight lines. Okay. Anyway, so but we will need to use this popsicle moduli space and this strange codimension one kind of obstructions to prohibit obstructions for the existence of Ampere structure. So Abujay-Saida already has a very good Ampere structure for their theory. But this kind of new stratum we have to show that this new stratum does not arise. And we have a theorem with Choa and Jeong, which roughly says that in some special cases they don't arise. Popsicle is arise if maybe I need a bigger space. Yeah, let me. Which part do I want to? So this is first M is revealed, and Reeb flow of boundary M defines free S1 action, and then this, so on boundary M. So boundary M is kind of filled with, it's covered by this Reeb flow S1 orbits. So this boundary, the fundamental class, give rise to some symplectic homologous class, gamma. So if you don't know what is this, then just imagine that boundary has this S1 orbits, and gamma is a class which represents these orbits. And then if, so this crucial condition is that if the Robin-Solomon in some index is non-negative, then popsicle spheres do not appear. All right, so suppose we can now kind of ignore this kind of strange stratums with popsicle spheres. Then how do you define this new of this common class gamma? We are going to insert gammas here. And so what is this new category C? Gamma of M. It says the objects of this new category are the same as Fukaya category of M. So it's just compact or non-compact Lagrangians equipped with some brane structures. And the morphism space of two objects, the L1 and L2, is given by this wrapped flow complex of L1, L2, epsilon, Ericsson wrapped flow complex of L1, L2, where epsilon is a formal parameter with degree -1 plus n minus, anyway, so this is some degree of gamma. So this is a wrapped flow complex. We just put two wrapped flow complex here and put an epsilon here. And the point is that the new differential is going to be something which is inside of this component, the standard differential of the wrapped flow complex, standard differential of the wrapped flow complex. And there is this differential which is given by inserting gamma in the middle. So this is called, so in picture it looks like this. You have some gamma, you look at geometric maps with interior insertion of gamma and some input and output. But gamma has to be at the center of this disk. And this is called quantum cat action. So this is quantum cat action. So somehow, what is the cohomology? So cohomology of M1 is this cohomology of this delta 0, 0 cat gamma. So what happens is you're actually killing the images of this cat action. So that's what it is. And higher if you know Abzai-Saida, you probably know how to extend this to higher operations. I don't know if I want to do it. Maybe.
So the gamma is the wrap orbit that wrap around once around E.
Right. So right. Gamma is that's good. Right. So so there's a device D. So we have this normal bundle, and so there is a kind of orbit, S1 orbit, which is wrapping around the divisor, and the fundamental class of this is going to be in M. Okay, and so if I write element here as A plus BI, then B epsilon, so A plus B epsilon, so standard component, like epsilon component. So MK on standard components is the usual MK on AIs, but MK on maybe some of the AIs, but then some if you have BI1 epsilon, BIS epsilon, and AK, then this will have two outputs, one without epsilon, the other one with epsilon, and this one is given by this kind of counting disks with BI1 to BIS output. Whenever you see epsilon, then you kind of draw lines and insert gamma. And here the same. But here you're going to forget one of those. So maybe you can just forget. Just don't insert either upper one or lower one. It looks strange, but somehow this defines an AP structure. So this was already in Abzai-Saida. I mean, the algebraic structures are similar, so that made us skip. And also, Saida observed that this has one parameter family of deformation given by just modifying M1. So let me call it M1 lambda. This is just by lambda times identity. And it still works. So this lambda, then this C gamma lambda is an infinite category.
So can I ask something?
Yes.
So I don't know, maybe you said it. So this construction already Paul did this, right? Paul already did this construction in one of his left shift papers.
You mean this one? No, to have these insertions, you need this few moduli space.
I was going to ask, maybe your theorem is that in this example sphere, I feel like I've seen these moduli spaces too. In one
Right. This is here.
So those yes.
Yeah. But this one I don't see. Maybe you can tell me.
If there is no sphere number, what is the difference with
If it's the same. Yeah, I mean the algebraically the boundaries look the same.
Interpolate between these two. He gives two different interpretations of.
Yeah, I know what you
points,
mean.
Right?
But not this one. I don't know. It's not. Yeah, he used some intersection numbers and so on. But I don't know if it's the same.
Yes.
I don't know if it's the same.
But maybe with this. Okay. Anyway,
yeah, but this one.
Omeliano, they now also have the insertion version. Maybe.
This is actually quite complicated. I don't know whether.
No, I'm just.
I don't know whether they
place
did
it.
Oh, yes. So there is one parameter family of infinite categories. So there is this choice of lambda in C. So you can choose 0 or any number, but which one to choose, right? So you get different categories. So that now let's go to the divisor components.
Yeah, maybe I'm also not getting it. So what's the point of introducing these popsicles with insertions? Why not taking the other one? Why was that not good?
Because if gamma is an input, you cannot really do that. Right? When you compactify the moduli space,
You're just using the same moduli spaces for a different purpose.
no, they are different moduli spaces.
Oh,
That's,
sorry.
that's exactly what I want to say. So when these are inputs, you cannot really say.
You cannot merge
You
them.
cannot really say. I mean, you're looking at maps like this. Anyway, so it's maybe yeah.
I see.
We can talk later.
So I was Seidel did not have the sigma model. The sigma
Right,
concept.
right.
They did something.
So what they did was they put
Yeah, we don't need to.
Yeah.
Don't waste time.
they put some homotopy data here.
Mhm.
They use it to place some homotopy data. Of course, you can put
Mhm.
add homotopy data.
No, but
next to
that's
your
the
overlay.
earlier paper. It's from 2007. There are many papers after that, and I think he also put other things there. But you're saying this issue.
Well, I
is
talked
not right?
to Paul.
No, it's just, can you explain? I think I also didn't understand this point that you made about, like, why is it so crucial?
Because
It's,
you need
it's not right.
you need the compactification moduli space to define anything. They have a very strange compactification. Like you need to first describe all the codimension one straight terms, but that's not the standard compactification. This is not like Gromov-Witten type because this
Non-stable maps.
this is not stable map. You need a new notion of compactification. That's why. But I can explain you more. Okay, so let's go to divisor components. So it's been observed there's this free S1 action on this this disk normal bundle of B. So we can define gamma in this divisor component, and one proposition is that this only gender index of gamma is index n plus tau d divided by k, and this is positive. So somehow we can define. Well, it's not Robin-Solomon, but anyway, Robin-Solomon is positive, so we can define this sigma lambda m. And in this case, degree of gamma is given by negative 2 tau d divided by k. Let's keep this here. Okay, so now we have this in M. We have this S kind of gamma here. So this orbit here is gamma, and so how do we? So now we have, suppose we have this Lagrangian L. We want to map it to the Lagrangian in D. So that's the Lagrangian correspondence. And so now this was a Ruby domain. Now you complete, which means you kind of add the color, kind of cone completion. And so suppose you have this cone completion and multiply D because you want to go from M check to D. So of course the correspondence somehow we want to use the product space and Lagrangian inside there. The Lagrangian C is going to be kind of circle bundle over D. So this C is going to be X and pi X, where X is in boundary of M. So at this boundary, this X is an element of this completion. Also, X, you can project it to the divisor. So that's, and this is, you can check, because there is a kind of circle worth of fibers. This is the S1 vibration over D. Okay. And lemma we can prove is that if D is simply connected, then C is in fact monotone. Monotone Lagrangian submanifold. So monotone Lagrangian means symplectic area is proportional to the Maslow index of the disks. And so we can learn, and we can run this Lagrangian correspondence. So this Bernheim Woodward, there is a Lagrangian correspondence. So somehow you pull back and just project. It's usually immersed, but we assume that it's embedded. So let's say you have Lagrangian K, you send it here. So assume that this is embedded. So D is monotone, this Lagrangian is monotone, so flow homology is well defined. So we want to now kind of look at the map between them. So that's where we started. And in fact, this, maybe if you haven't seen this Lagrangian correspondence is on the level of object observed by Einstein, and with Bernheim Woodward defined it as a functor from Fukaya category of M check. Let me be careful. So if all these are monotone, then you have this functor, right? 2, Fukaya category of D. But now there are some works which you can extend it to Reeb Fukaya. So this is the correspondence. Let me say this, and this correspondence is usually counting of this kind of moduli spaces. Suppose you have some Lagrangians K1, K2. Then this is C, and this diagram is supposed to represent that there is a map U1, U2, which mapping to this guy maps to this completion, and this guy maps to D, and this C is supposed to tell you the kind of the boundary condition of U1 cross D, U1 cross U2 along C. And that's, I mean, if you haven't seen, if you're seeing this first time, just maybe you cannot really understand it.
I'm getting a little lost with the notation.
Yes.
So the C was the corresponding Lagrangian.
C is correspondence, right?
But what is C composed K?
That's the image of this correspondence will take some Lagrangian here.
Oh, I see.
To
The K, because there was
C of
another
K,
K before, but there was an integer. Capital K.
All right. So, oh yeah, we're almost there. Right. So we have these maps, but now we want to do something else. What do we want to do? So here we have a gamma here, which was this. I mean, not. This is a symplectic homology. So gamma is a symplectic homology class on M check, and we want to think of it as a symplectic homology of the whole thing. So and check the completion of M with D. So this is exact, this is monotone, so you can think of it as monotone. And you can define stereosymplectic homology, this guy. And we want to just think of this element, which is given by gamma tensor unit. It's important to describe the almost complex structures as well, but let me just ignore this issue. Then the first theorem is that so the closed open map should be taking an element here and you send it to some Fukaya category of M check plus D, right? So so this and C is a Lagrangian here, so there is a closed open map from here to here. So this the closed open image of gamma tensor is ED. So this is going to be this is a multiple of unit. EC, and this multiple is denoted by sigma. So this multiple is sigma. So this theorem is in fact a non-trivial theorem because closed open image can be anything in flow homology of CC. So flow homology of CC, there are many elements, and we're just claiming that this is a multiple of a unit class, and the coefficient we are denoting it by sigma. Okay, and then so now that's the sigma is the lambda that we want to use. Then if we choose this sigma, the theorem is that there exists an infinite functor from C gamma sigma to the Fukaya category of D. So Fukaya category of D, taking K to the Lagrangian correspondence images. Right. All right. Okay, what happens? So what happens is that this is an infinite functor, and how do we define infinite functor? So we add kind of popsicle. We consider popsicle cubes. So we have some gamma class here.
Don't take it too literally.
All right. So we have some insertion of gamma class here, and some kind of moduli space like this. The point is that when this guy hits this point, we get sphere bubble, but this sphere bubble is in fact a disk bubble with insertion of gamma. Because as you said, this is a product space. You can actually think of it as anyway. So this you can do. So this is in fact sigma times identity. So it's crucial that the sigma came from this closed open map of gamma times this one. So when this guy hits here, you have sigma. So that's somehow this. So if you do not have the correct sigma, then this moduli space will not define a functor. So only with this sigma, this defines a functor. And so what happens in the example? In the example, what happens is that in this RT3 example, gamma is kind of half rotation. Remember that this was kind of rotation on the divisor, and RT3 this is like half rotation, and we are using the fundamental class of all the periodic orbits, so it's like fundamental class. And so this corresponds to xy. And then the close open image, close open FC of gamma times ED is t to the minus 1 half of BC. So we have this one. So finally, what you get is this relation on C gamma sigma, we have this cap gamma equal to minus cap gamma minus lambda times identity kind of becomes 0. So it becomes 0, and this cap action is something like xy, and sigma is something like t to the negative 1 half. And so this relation xy equal t to the negative 1 half was the additional relation that we have imposed to make it into an isomorphism. If you remember, we added some strange relation xy equal t to the negative 1 half to the Reeb Fukaya category, and then this becomes an isomorphism. So,
can you say again where did this come from?
So, yeah. So the usual Lagrangian correspondence just goes like this, right?
I got the thing with the EC. I got the thing with the EC that it was multiple of EC.
This one.
Yeah.
You
So then how do you get this from there?
From there. So this cap action, so this cap act on K is like xy times identity. So cap action is, this is xy times identity. This is t to the 1 half times identity. And they are and then you are looking at the cone complex, cone of this operation. So this means you're kind of identifying these two in the cohomology. So this becomes the same. So xy becomes t to the negative 1 half.
How does sigma relate to t to the minus 1 half?
That's this close open map.
Where's sigma in that map?
This is sigma. This is. So we have the usual Lagrangian correspondence, and then on the boundary we have this gamma orbit, and then you kind of use it to modify everything. So Reeb Fukaya category, you modify it into sigma, and this functor, you add to this standard functor this this popsicle fields. Then even with this modified category, you still have the infinite functor, and this one becomes an isomorphism in this system. So this is
So how does sigma added into your picture?
sigma is the closed open map of this on C. So originally gamma is a simplex commutative here. You think of it as simplex commutative by multiplying identity fundamental class of this one, and then it's going to act on any Lagrangian here, right? So the closed open image is kind of sigma times identity. Yes. So yeah, on C, this gamma looks like sigma times identity. So the gamma effect becomes sigma. So gamma effect. So this gamma action is sigma. So that's what happens. And that's, if you give that relation, then you get nice one. So this has the effect of modifying the non-compressive, make it look more like.
Okay, let's thank the speaker for his insightful presentation.